A good approximation of the normal weight of a person 60 inches or taller but not taller than 80 inches is given by W of x is equal to 5.5x minus 220. So we have a relationship between the height of the person and the weight of the person, right? So we have a relationship given by over here where x is the height in inches and W of x, so this function is weight in terms of the height, right? And it's in terms of pounds. So our goal here is to describe how the graph of the function W can be obtained from the graph of one of the elementary functions. So we have learned a couple of elementary function earlier, like y equal to x, the identity function, y equal to x square, the square function, q function, right? And then absolute value functions. There were a couple of elementary function we learned. So by using that, we need to show how this the graph of the function W can be obtained. So let's try to see that. And we also need to sketch the graph, so we'll do that. Alright, so what is happening here? So this is the weight function we have given here as 5.5 times x minus 220. So by looking into the graph, which one is the elementary function that looks like given over here? Certainly we have this x over here, so we can say that the elementary function is x, right? The identity function. So that's what we have been given over here. So we have the identity function, but if you look into it, the identity function x has been multiplied by 5.5, right? So that's what it is given over there on the first term at least. So but we know that if we multiply by any number which is, let's say, greater than 1, so that's what happening in this case, right? 5.5 is a number which is greater than 1, and that has been that has been used to multiply that identity function. So it says that this is a fact. It says that if we multiply by a number which is greater than 1 to the function, then the graph of the new function will be stretched vertically by a factor of c. So that means so if the elementary function is x, so if we multiply by 5.5, then the graph of the identity function will be stretched vertically by a factor of 5.5, right? So that's what it means. Okay, so what we can say is right now the elementary graph was y equal to x, the identity function, we stretch that vertically by a factor of 5.5. Right, so let's try to see what is the extra thing we have over here. So 5.5 times x, we have been given that 220 is subtracted from that, right? So what do we do with that then? Well, if we subtract a number, let's say a positive number, to the function, so that's what it is happening. We have been subtracting 220, let's say, from 5.5x. So if we do that, it says that the graph of the new function will be shifted down by the c unit. So on this case, then whatever is the graph of, let's say, y equal to x, we vertically stretch by a factor of 5.5, and then we shift that down by the 220 units, right? So that's what it means. Okay, so what we can just say here is the elementary function y equal to x is vertically stretched by a factor of 5.5 and shifted down by 220 units. I want to say that this is the graph of the function. But how did we obtain this graph? We basically discuss over here, but I want to show you step by step how we obtain over here. Okay. Alright, so let's go ahead and then revisit this problem again. So originally, this was the function we needed to sketch, but we saw that the elementary function here involved with is the identity function, whose graph is this, right? So this is the identity function y equal to x, and now let's we have to multiply by 5.5 to the x. So that means, what did we say earlier? We need to stretch vertically by a factor of 5.5. So let's do that then. So this is the graph of the function 5.5x, which is obtained by vertically stretching the identity function by a factor of 5.5. We can notice that over here. You can see over here at x equal to 50, the y value, or the, on this case, sorry, w value, the weight value is around here is what, 50, right? So for 50, the w was 50. But on this case, what is happening over here is for corresponding to 50, we have, this is somewhere over here. If we, this is 50, this is 200, so this is 250, somewhere over here. Probably that is, what is 5.5 times 50, is that 275, something like that. Can you confirm what is that one? So 50 times 5.5, what will be that? 275, right? So it's exactly happening somewhere over here on 275, it's intersecting, so the for this function w is around like at 275 corresponding to 50. That means we are stretching by a factor of 5.5. So this is the graph of 5.5x, but we need to obtain the graph of 5.5x minus 220. So you can see here clearly then this is the graph of the 5.5x minus 220. Why is it like that? Because we are shifting this graph that was passing through the origin 5.5x to the 220 units down over here. So when we shift it down, we get the graph of y equal to 5.5x minus 220, right? So but our goal is to write down the graph of the perfect this weight function that is given over here. Isn't that the same function? Yes, it is. But I just want to just revise the given question. You can see here on the given question it says that a good approximation of the normal weight of a person 60 inch or taller but not taller than 80 inch. So we have actually also given some explicit domain here. The x value is actually has to be greater than or equal to 60 and less than or equal to 80, right? So that's what it has to be. So that's why I try to just draw the graph of the function y equal to 5.5x minus 220 only between 60 to 80, and then that's the perfect weight functions graph for the given function.